Hi, and welcome to our presentation. Thank you for attending virtually due to the COVID-19 pandemic. My name is Preston Sanderson,
And I'm Kaushik Shah.
and our research is a forecast of the S&P 500 index. We did this research in the Dillard College of Business Administration at Midwestern State University with our professors, Dr. Pablo Garcia Fuentes and Dr. Joseph Smalley. The S&P 500 is a stock index that tracks the stocks of 500 large cap U.S. companies. The S&P 500 is a good indicator of the U.S. economy. Investors use the S&P 500 as a benchmark of the overall market to which all other investments are compared. In this research, we focus on forecasting the price of the S&P 500 index. The objective of this research is to forecast the price of the S&P 500 index using ARIMA, autoregressive integrated moving average forecasting method. Researching the S&P 500 is important because it is arguably one of the most important stock indexes. We are using the daily data period from January 4th, 2016 to April the 16th, 2020, which we obtained from the Fed St. Louis website. In this research, we have used the autoregressive integrated moving average ARIMA procedure to analyze and forecast the S&P 500. The method allows for predicting the future values of the S&P 500 based on the combination of its past values and past errors. We follow the three stages of the ARIMA modeling: identification, estimation and diagnostic checking, and forecasting. To forecast the S&P 500, we use a seasonal ARIMA 112-1127 model. The mathematical model is given on the slide, where T is time, B is the backshift operator, is the S&P 500 index, is the moving average parameter, is the autoregressive parameter, and is the independent random error. In this slide, you can see the plot of the S&P 500 original series, and this gives an idea of the behavior of the series over the period from January 2016 to July 2020. The table on the left shows the descriptive statistics for the S&P 500. The total number of observations used in this analysis are 1,079. So we conducted the identification of the log of the S&P 500 based on the figure trend and correlation analysis on the right of the slide. The autocorrelation function, ACF, does not decay as the lag increases, and the PACF shows two significant lags. The ACF and the PACF plots suggest an AR process. In addition, the table autocorrelation check for white noise shows that the p-values for the 36 lags of the series are highly significant, so the white noise hypothesis is rejected, as it is usual for non-stationary series. Also note that the IACF shows no over-differencing. The original S&P 500 series is non-stationary, and the errors are highly correlated. The table on the bottom left shows the descriptive statistics for the first difference of the series. The figure on the right shows the ACF decreases very rapidly. This implies that the first difference of the S&P 500 is stationary. If you look at the partial ACF and inverse ACF graphs on the bottom right, they suggest that an autoregressive of order, or AR model, the PACF and the IACF also suggest that there may be seasonal effect. This means that there are some lags that are non-zero. In the last procedure, we had 1,079 observations. And in this procedure, as you see, we have 1,078 observations. We lose one observation, or the first observation, as we are taking the first difference. The chi-squared values in the autocorrelation table on the bottom left are highly significant. Hence, this shows the S&P 500 is highly correlated. Hence, an autoregressive of order 1 model, AR, may be ideal to model this series. The first difference of the S&P 500 series is stationary. The errors are highly correlated.
As Preston said in the earlier slide, that there are some seasonal effect, that is, There are some lags that are non-zero, hence we'll have to do 7-day seasonal differencing. In this slide, we show the stationary tests. To test if the S&P 500 series is stationary, we conduct the augmented Dickey-Fuller or ADF test and the Phillips-Perron or PP test. The ADF and PP tests are conducted using zero lag differences because the identification test suggests an autoregressive model of order 1 or AR1 model. So the ADF and PP unit root test tables on the right are for zero lags. Now look at the p-value on the tau statistics on ADF and PP test on the right-hand side of the slide. The p-value on the tau statistic is more than 0.05 or 5%. Hence, the hypothesis that the series is non-stationary is not rejected. Also, the ADF and PP tests show that the original S&P 500 series is non-stationary. This slide shows the stationary test on difference series. The ADF and PP tests results are shown on the right-hand side of the slide. The ADF and PP tests are conducted using zero lag differences because the identification test suggests an AR1 model, just like we did in the earlier slide. So the ADF and PP unit root table show the test for zero lags. We focus on the trend model for the test, which is highlighted in yellow. Please note that the p-value on the tau statistics is less than 0.01 or 1% for both ADF and PP tests. Hence, the hypothesis that the series is non-stationary is rejected by both tests. And the first difference of the S&P 500 series is stationary according to the ADF and PP tests. Now we'll do the diagnostics to identify the ARIMA models. The identification stage suggested that an ARIMA 112 model, which is a process made up of AR1, MA2, and a seasonal moving average. To verify that this is appropriate model for S&P 500 index, we conduct identification tests. We use the smallest canonical correlation method, SCAN, the extended sample order correlation function, ESACF, and minimum information criterion tests, MINIC. The table below in the slide shows that the three stages suggest an AR1 and MA1 as indicated by the identification stage, where P is 1, which is the order of the autoregressive process, D is 1, which is the level of difference, and Q is 2, which is the order for moving average process. In addition, P plus D is 1 plus 1, which is 2. So this suggests an ARIMA model of ARIMA 112. And the SCAN test suggests that ARIMA 212, and whereas ESCAF and MINIC tests suggest ARIMA 112 model, and hence we will be using ARIMA 112 model. This slide shows the forecast of S&P 500 index using the ARIMA 112 by 1127 model. The selection of this model was based on the tests that we did in the earlier slide. The conditional least square estimation shows that ARIMA model parameters estimates are significant at 1% level, or the p-values are less than 0.01. The estimated seasonal ARIMA 112 by 1127 model for the S&P 500 index is shown in the slide, where T is time, B is backshift operator, and ET is the independent random error. And as you can see, the ARIMA model estimates are significant. This slide gives the forecast of S&P 500 index. The graph shows the within sample forecast and the outside of sample forecast of the ARIMA 112 by 1127 model. The dotted points are the actual values of S&P 500 index. The straight blue line is the forecast of S&P 500, and the blue shade is the 95% confidence interval. The within the sample forecast is for the period January 4, 2020 to April 16, 2020. Note that the predicted values follow very closely with the actual value, which also indicates that the model fits the data well. The blue line from April 16, 2020 to May 6, 2020 is the actual forecast for the S&P 500 index that we got from our ARIMA 112 by 1127 model. In this slide, you can see the data table for S&P 500 index forecast from April 17 to May 6 of 2020. Conclusion, for the forecast of S&P 500 index, we used ARIMA 112 by 1127 model. Based on the model, the S&P 500 index is expected to decrease. But please note that the model does not take into consideration the effect of coronavirus pandemic and the oil market crash, which happened on April 20th. We hope that we return to a normal energy market soon. Getting back to this model uses past data to forecast future data, and therefore it is difficult to take into consideration unpredictable events like the COVID-19 pandemic and the oil market crash. Thank you everyone for watching our virtual presentation on forecast of S&P 500 index. We would like to thank Dr. Garcia Fuentes and Dr. Smalley for mentoring us and teaching us how to use the SAS program. And we also would like to thank EURECA at MSU Texas for giving us the opportunity to virtually present our research during this unfortunate event. Thank you.